So I thought that I would start by sharing this visually stunning set of maps made by Eric Fisher. Every once in a while an amazing map idea surfaces, and I think this is one of them. These maps show every Flickr geocoded location in the last 10 years for each one of these cities. But wait, there's more. Each photo location is then linked according to the user that took the photo. And the lines connecting the geocoded photos is color-coded based on the rate of travel between the two locations. The cartographer, Eric Fisher, was interested in identifying popular routes for riding his bike in these cities, to see the sights. He explains it like this: a cluster of geotagged photos is a good indicator of the interestingness of a place because it signifies that people, first of all, went there, and second, saw something worth taking a picture of, and then put the extra effort into posting it online for others to appreciate. So he looked for densities of these things, but he wanted to be able to ride his bike, so he looked at the rate, the travel speed between the photos and color-coded. So the black lines indicate walking speeds, and the red lines indicate speeds between 7 and 19 miles an hour. And you can see in some of these, like this is San Francisco, a lot of these are ferries, boat travel, which is pretty interesting. Yeah. Okay, so I'm going to give you a map blitz of a bunch of fairly traditional map types, and I'm hoping that you're going to see something that inspires you, a map type that you want to learn more about or want to learn how to make for maybe your final project. So the first one is dot maps. Dots here represent a number of things in each area, and they're placed randomly within that area that's being measured. It's one way to show density. Another one is called graduated symbols, and this is a way to show counts per area, like a raw count, population or number of schools per county. The symbols are sized based on an attribute value, but they're not always proportionally accurate. Proportional symbol would be the other choice there. Some of these maps you're going to have seen 1,000 million, shillion times. Topographic maps are really common navigational landscape maps. They show natural features, landscape details, roads, towns, and notice the hill-shaded relief as the base map. Contour maps also show topography. They can map elevation or temperature or densities. In contour maps, the lines join points of equal value, and you have, I'm sure, seen these a million times. Maybe not shown in 3D like this one, but you get the idea. Okay, surface maps. Surface maps are interpolated, meaning the values are filled in between locations with known or measured values. These are really commonly used for precipitation, temperature, densities, elevation, slope, wind speed. It's pretty common stuff. You have definitely created these and will definitely create more. Voronoi, that's how I call it. I'm not sure if that's exactly the right pronunciation, but these maps show which features are closest. So basically, if you look at the polygons around each point feature, this area is the area most proximate to this point. And as soon as you cross over into this polygon, now this is the closest point. Does that make sense? So here, if you're still right here, this is the closest polygon, but the second you cross over this line, you've moved closer to this one, and it's as the bird flies. These are often used for determining resource allocation, things like that. Like an ambulance might want to know which hospital is closest, something like that. But again, it's as the bird flies, so you have to be careful. Vector direction maps. These use magnitude and direction fields in a data set to map, raster data with vector symbols instead. Magnitude encodes the arrow's size, and direction encodes the arrow's angle. These are used for wind speed, currents, things like that. But you do need to have a two-band raster showing direction and magnitude, or angle and magnitude. Okay, distributive flow maps. These are actually possible now in ArcGIS Pro. So are vector direction maps. You can do both of these in ArcGIS Pro. There's a tool called distributive flow, and I've never actually used it, but I do hope that someone will try and employ it for their final project. It's kind of like mapping a budget. The line width encodes quantity. The paths aren't specific to actual travel. It's just more like a visual budget. They're pretty cool. Okay, hex maps. These are the new mapping rage. You know how in a map of the United States, Columbia and Rhode Island just always get lost, and Texas and California and Alaska are completely overrepresented because they're so big? Well, hexagons can replace state outlines, which results in a map that still looks like the US and maintains those geographic proximities and relationships, but the areas are treated as equal. And you could use some other shape like squares or something, but hexagons look cool, and their geometry is a little bit more flexible. You can have things going off to the diagonal, just not limited to up, down, left, or right. So, but think about that. Equal areas are really an important consideration when you're mapping quantities that aren't already normalized by area or normalized in some other way. So switching to a hex map is just a really great way to normalize the data without actually having to change the values by calculating percent or rate or density. Okay, firefly maps. These were invented by an Esri cartographer named John Nelson. And I would recommend that you take the time to Google John Nelson. He's amazing and an incredible resource for cartography and cartographic instructions. His job with Esri is to basically spend all day geeking out on cartography. And then he blogs about it. And he posts video demonstrations and written step-by-steps. He's ridiculous. John Nelson, make sure you check him out. Firefly maps are basically just a symbology technique. It's a point file, and some attribute field is changing the size of the glow. This is something that you can do in ArcGIS Pro, but it's not automatic symbology. It's something you have to mess around with a little bit. Okay, here's just so you know, John Nelson. If you Google him, you can often download his symbology as a style and then just plug it into your maps. So it's not contained in ArcPro, but it's something that you can access and download really readily. All right, cartograms. Cartograms are another way to equalize area and normalize the data when you're mapping raw counts. So the boundaries between features get glued together, but the areas within the polygons are scaled proportional to some attribute value, like the number of swimming pools per state or the count of drunk driving arrests. It's not like you wouldn't use a cartogram if you're mapping Starbucks per capita or deaths per 100,000 people or dogs per square kilometer. Those are normalized values. But if you're just looking at a raw count, cartograms can be a way to do that. The other caveat with cartograms is you really need to use areas or features that are super common to people and people are really familiar with. I've seen students make cartograms of the Utah counties. And even if you're super familiar with the county map of Utah and you've been looking at it your whole life, it's almost impossible to make sense of what you're seeing when you start distorting the shapes. We're so familiar with the map of the contiguous US that it's still pretty easy to see what's going on, that the upper west is collapsing, whatever this is a map about, I don't know. Okay, heat maps, point density maps. You see these when you're looking for like a sweet Airbnb in some city. You can turn on cultural landmark heat maps or restaurant heat maps to see densities displayed this way. They're calculated from point locations, and you're going to get a chance to make heat maps later in the semester. Space-time cubes are so cool. These map changing values over time and over space. So older values are on the bottom, newer values are on the top, and you can see how values are changing over time in geographic space. It's a super unique mapping technique, but not terribly useful. And a lot of people would say that it would be nice if Esri put their efforts into fixing the, negative 99999 general error instead of building stupid symbology things like this. Let's just fix the crap that we already know is broken. Okay, isochrone maps. Isochrone maps are just like Voronoi polygons, but the opposite and much more complex. So these are used by emergency responders, basically from any location or from a set of features on a map. It calculates how far you could travel in a given amount of time using a second layer like roads that might promote or impede travel. And you could even incorporate attributes from that second feature class like speed limit or slope to affect the rate of travel. And that's why they're not uniform shapes, because they're being affected by some other feature layer. So you may not be able to see this on this map, but each little point here is a pie chart. And, pie charts, we can talk about those another day. But, the idea of a data visualization is upping the complexity and increasing the data density on a map. So you could have a choropleth map like this that's mapping some attribute value, but maybe you're adding a secondary data set and displaying it this way where you're allowed, to kind of create compound maps. You could add a bar chart to an empty space on the map that helps tell the story of the data. And finally, ye old choropleth map. A choropleth just means you're coloring in the area and the color represents some attribute value. These are, beware, only appropriate for mapping normalized data. You can map rates, percents, densities, but not raw counts with a choropleth map because the area imparts too much bias. Small things get buried, big things get blown out of proportion. So no raw counts, normalized data only. Okay, so then let's talk quickly about two different types of maps. There's reference maps and thematic maps. Navigational maps are reference maps, road maps. You've seen these a million times. Topographic maps. But thematic maps feature a message. And in this class, you're going to be making both types of maps. But typically, you'll be making both. Thematic maps, think of them as topical maps. They have a message. And the important thing is to only include information that's necessary to conveying your map message. Focus. Leave all other stuff off. You can obviously have compound maps and have lots of data on a map, but that should be the map's purpose and the map's message. It should support it. Don't just put, north arrows on here just to have it. Don't include stuff that you don't need. And we'll talk a lot about focus as we move in here. Thematic maps, it's just worth mentioning that they can display qualitative data like state names, land cover type, politics, and ordinal data like rankings, right? Suitable, unsuitable, moderately suitable. Or they can map quantitative data, which can either be classified or continuous. Continuous data is going to apply a stretched color scheme, and classified data is going to bin the values into groups. And then each group gets a particular symbol size or a color that ranks that class in some kind of order because it's quantitative numeric data. And finally, no pressure, but keep in mind that maps are a really unique way to communicate science. Every piece of the composition is data. Everything that you put into your layout is communicating something that needs to be working in support of the map's main message. So let's talk about how to compose a good map, and we'll do that in the next set of slides.